In today's lecture, we're going to talk about biogeography and plant distribution. I'm going to start off with one of my favorite pictures from one of my favorite parts of the world. These are Copiopoa clummed alba, cacti that orient due north at a particular specific angle that maximizes the amount of radiation at the tip and minimizes the amount of sunlight on the sides of the cactus. They are found in the Atacama Desert of northern Chile, one of the driest parts of the world. In today's talk on biogeography and global ecology, the fundamental concept that we'd like to get across is that there is a strong relationship between plant community type and the environment. Here in part 1, let's go over the fundamentals of geography and climate, where we can talk about how sunlight or solar radiation and wind determines the climatic zones. The greatest amount of sunlight on Earth is received directly at the equator. As we move farther north away from the equator, the amount of sunlight striking that surface decreases because there's an angle change. And so the intensity of light striking that surface is actually a function of the cosine of the latitude, so that there's less sunlight striking the northerly latitudes than there is at the equator. This sets up temperature gradients, and it'll also drive water evaporation gradients. As moisture evaporates in equatorial regions, it rises up, and when it gets to a certain height, that moisture falls out, forms clouds and falls out as rain. But the air that moves upward also moves northward, or it moves in a southerly direction, forming a cell. As it moves north, there's a rainout of the water in those clouds, and eventually that air mass descends. The air mass arises at the equator, the rainout process occurs, and that air descends, creating high pressure regions at about 30 degrees north and 30 degrees south of the equator. As that air descends, it rushes back towards the equator, where we have this cell or cycle, that air cycle that's being developed. The cell between 0 and 30 degrees is known as the Hadley cell, whether it's north or south of the equator. We see a similar pattern between 30 and 60 degrees north and 30 and 60 degrees south, and that's known as the Ferrel cell. And lastly, there's a third cell of air movement known as the polar cell that occurs between 60 and 90 degrees north. There are also circulation cells that are driven by the directions of the prevailing wind and the rotation of the Earth. We have seasons. The climate is not constant because the Earth does not rotate on a direct north-south axis. It's actually tilted at about 23.5 degrees. So twice during the year, September 22nd and March 20th, we have exactly 12 days of sunlight, 12 hours of sunlight and 12 hours of darkness at all latitudes. That is known as the vernal and spring equinox. As we move past the spring equinox in towards the summer, more of the northern hemisphere faces the sun more directly and less of the southern hemisphere. So that in the northern hemisphere, June 21st is associated with the point at which the maximum tilt towards the sun is achieved. And likewise, as we pass back through the autumnal equinox, we have a winter solstice, which is the shortest day of the year and the least amount of radiation in the northern hemisphere, but the opposite or most in the southern hemisphere. So over the course of a year, we go from a time period where we have equal day and night, that's the vernal period, and then we enter into a summer solstice. Then we have the autumnal equinox, followed by the December or winter solstice. Without this tilt, we wouldn't have seasons. So because of this tilt, which gives the northern hemisphere more radiation at some times of the year and the southern hemisphere more radiation at the other times of the year, we have seasonality.